Hello everyone. In this example, I want to look at the idea of heat transfer within a system, or at least in a closed system. And we're specifically going to look at if you have a insulated container that has a specific amount of water at a specific temperature, and you take, for example, a block of metal, in this case copper, that has a high temperature, and you add it to the water and allow thermal equilibrium to be reached, what will happen? Right. And of course, I already said it. So thermal equilibrium will be reached because our situation is something like I drew here at the bottom. We have an insulated container, right? This contains our water at its initial temperature. Water has a specific heat capacity. We then add copper, specific mass, specific temperature. But because of the insulated nature, the closed system, there can be no heat or matter exchanged with the outside. Right, so the only place where the copper's heat can go is to the water. In other words, the copper can only lose heat and the water can only gain heat, and nowhere else can anything go. So all that we expect to happen is that the copper block must give off heat, and that heat must be the negative of the water, or the water's absorbed heat must be negative that of the copper, like I wrote here. So that's what we expect. And we expect that the one's temperature is going to decrease, the copper block's temperature should decrease, and the water's temperature should increase. Okay, until a point where thermal equilibrium is reached. And what does thermal equilibrium mean? That is when the temperatures of the species are the same. And we can just give it a general symbol TF. So TF of water is equal to TF of copper, which we just call TF. Okay, so how do we calculate the heat of a substance when it remains in the same phase? Well, the heat of water is equal to its mass multiplied by its specific heat capacity, by its temperature change, and the heat of copper, of course, by its values. The mass of the water we can get from its density, and like I did here, mass of the water from its density. And what we're given for copper is we're given its molar heat capacity. In other words, we don't need the mass like we do for water. Here we need the mass of water to go with the specific heat capacity of water. We need the number of mole of copper to go with the molar heat capacity of copper. Right, because it goes with joule per Kelvin per mole, whereas water goes with joule per gram per kilogram. So you just check what the units are. You use the correct one. You then put those two equations into our water equals negative the heat of the copper. And you go through the effort of substituting in the values, right? Plug them in, plug them in, plug them in. And eventually you get to the point where you remind yourself, well, that the temperature change of these two things, the initial temperatures are different, right? They're the individual temperatures, Ti H2O, Ti copper, but their final temperatures are equal. So we can just call that TF. So we can get to this expression that I have here at the bottom. And this expression that I have here at the bottom then allows us to solve for TF, and that gives 39.5 degrees Celsius. And as you can see, that means the water's temperature only goes from 20 to 39.5 degrees Celsius, but the copper's goes all the way from 425 degrees Celsius to 39.5 degrees Celsius. So that means that the copper has had the larger change in its change in temperature. And of course, that is, as you know, from the fact that the heat capacity of the copper is smaller than the heat capacity of the water. You can see that in the molar heat capacity or in the specific heat capacity. You can go look up the specific heat capacity of copper. It's much less than water. In other words, water's capacity to carry heat per gram of the substance is much higher than that of copper's. Okay, so this example here just basically has 2 points. You need to remember that the only place that the heat can go is between the two substances, and they will be equal in magnitude, opposite in sign. We calculated using the MC delta T or NC delta T idea. And then they will have the same final temperatures, because then you can solve for the final temperature when you equate those equations. Okay. So I do apologize. I wrote this out earlier, and the music video didn't have sound, and I'm kind of lazy, so I don't want to rewrite the whole thing again. So that's why I'm just doing this. But I mean, now you have it as well, and you also have the explanation. So, all right. Thank you for watching as always, and I hope to see you in the next video. All right.